Yeah, so thank you very much for the nice introduction, Degwan, and thanks to all the organizers for making this conference possible. So before I start the actual talk, I want to give a 1 minute advertisement. So as Degwan said, I will be joining the KU Eichstätt-Ingolstadt in the new Institute for Machine Learning and Data Science in Ingolstadt, and there I'm looking for very motivated PhD and postdoc who want to join my group. So if you're interested in this, or if you know someone who might be interested in this, just send me an email and we can talk about the details. Okay, so now after this advertisement, let's begin with the actual talk, which, as the title says, is about the approximation theoretic properties of so-called complex valued neural networks. And in particular, the question is how these approximation theoretic properties differ from those of the usual real valued neural networks. So the talk is structured as follows. So in the first part, I will talk mostly about stuff that some of you will probably already know. So what is deep learning? What are neural networks? And then in contrast to that, what are complex valued neural networks? And I will also briefly review the approximation properties of real valued neural networks so that we can then contrast them to those of complex valued ones. So just as a brief or quick indicator, whenever you see this Mandelbrot picture in a neural network appearing, this means for me it's a complex valued network, whereas real valued networks will look like this. So then the main part of the talk will be about the so-called universal approximation theorem for complex valued networks. So there the question is, like, for these Legos, they are universal in the sense that you can build essentially everything out of them. And here the question is, under what conditions are complex valued networks universal in the sense that they can approximate any given continuous function arbitrarily well. And this means if you make them wider and wider while keeping the depth fixed. So and then in the last part, in some settings, it's interesting to look for more quantitative bounds. Say you want to know how wide do I have to make my network to achieve a given approximation accuracy. And some bounds like this can also be derived in the complex valued setting. Okay, so what brief introduction to what are deep learning and neural networks. So as you might have noticed, in the last several years, computers are now able to do a lot of things that would have been thought out of reach just like 5 or 10 years ago. So for example, if you talk to your phone, it will now, if you're lucky, actually understand what you want it to do, right? And as there have been similar breakthrough results in a number of areas. And all of these are based on this approach of so-called deep learning. And to explain what that is, let's briefly focus on the example of image recognition. So there you give the computer an image of something, and the computer is supposed to give you a label which describes what is depicted in the image. So and if you want to solve such a problem using deep learning, what you do is you first pay a bunch of grad students to take, let's say, 1 million of these pictures and give you the correct labels for each of them. Okay, so you now have a lot of label training examples where the XI are the pictures and the YI are the labels that you paid the grad students to produce. And what you then do is you set up a neural network of a suitable architecture and put into it these pictures. And then you compare the output of the network to the true labels that the grad students provided. And what you do is you then run your favorite optimization algorithm, probably a variant of stochastic gradient descent, to train the weights of this network. I will explain in a few minutes what this exactly means, such that on the training set, the network will perform well. So this empirical error, which tells you how well the network or how badly the network is doing on the training set, this will be made as small as possible. And then, surprisingly, it turns out that in practice, this works very well in the sense that the trained network will not just do well on the training set usually, but it will generalize, meaning that it will also work well on examples that it has not seen during training. But up to now, there is no comprehensive mathematical explanation of why this works so well. But if you want to understand this, the consensus is you should try to understand 3 things, which are called expressiveness, generalization, and optimization. So to explain what this means, let me briefly introduce the mathematical formalization of this learning problem. So you have a set X containing all possible inputs. So in our example, this would be all possible images, and the set Y of all possible labels. And on the Cartesian product of pairs, image and label, you have an unknown ground truth probability distribution, which tells you how probable each image is. So for example, if you look at all the images on the internet, then you will see that funny cat pictures are much more common than pictures of, let's say, Koshi or whoever. And given each image, it also tells you with which probability each of the labels is the correct one. So you should probably then predict, if you knew this probability distribution, you should predict the label with the highest probability, of course. And what you want to do is you want to find a function f which minimizes the so-called risk. So this means it minimizes the probability of doing something wrong. So the probability that your f predicts a label which is different from the true label should be as small as possible. But the problem again is you don't know this distribution, otherwise you would be done. You only have access to this distribution through a training sample. So through these images that the grad students labeled for you, which you assume are sampled independently according to this true underlying ground truth distribution P. And how this problem is then usually attacked is, or you have then 4 different functions. Let's start with this one here. So this fp star is the best function that you can possibly think of. So it's the minimizer among all measurable functions of this risk here. But in practice, you will not be able to work with a set of all measurable functions. So instead, what people do is they restrict themselves to a so-called hypothesis class, which in deep learning is just a class of all neural networks of a given size. So and then in this class, you have the function hp star, which is the minimizer of the true risk inside this class. And then the difference in risk between these 2 functions, between the true minimizer in this set of all measurable functions and the minimizer of the risk in this hypothesis class, this is called the approximation error. And this is related to the expressiveness of the hypothesis class, because if your class of, say, neural networks is very expressive, then you can very well approximate this function here. Okay, but then of course you again cannot compute this guy, because this is a minimizer of the risk, which you cannot compute since you don't know the ground truth distribution. So what you do instead is you minimize the error that your hypothesis does on the training set. So what you do is you compute the so-called empirical risk minimizer, which just is the function in the hypothesis class which has smallest risk or loss on the training set. And the difference between these 2 guys in risk is called the generalization error, because what you hope is that just by learning on the training set, the learned hypothesis will generalize in the sense that it will also work well on things that it has not seen during training. So and finally, this optimization error comes in because computing this actual empirical risk minimizer is a very hard, or in general, a very hard and non-convex optimization problem. So probably your optimization algorithm will not actually find the global minimizer, but something else. And then understanding this difference between these is called, or is understanding how well the optimization works. Okay, so long story short, you need to control these 3 different aspects. And in this talk, I will exclusively focus on this approximation problem here, which is maybe even the easiest of the 3 problems, but there are still a lot of interesting math that happens there. Okay, so now after all this talk about deep learning, I should maybe now tell you, since it all relies on neural networks, what mathematically a neural network is. So a neural network consists of a bunch of neurons which are arranged in layers, in different layers. So each of these neurons computes a real number, and how this precisely works is that each neuron in the input layer corresponds to 1 component of the input vector. And if you already know the output of 1 of the layers, you go to the next one by first applying an affine-linear map to the output of the preceding layer. And then to each component of the result, you apply a so-called activation function, which is just 1 function from the reals to the reals, which you fix once and for all for your whole network. And what people in practice are mostly using is this ReLU function, which just takes the positive part of x. So again, you go from one layer to the next by applying an affine linear map. Then in each component, this activation function, another affine linear map, and each component activation function, and so on. And the numbers in these matrices and vectors, which tell you how to go from one layer to the next in this affine linear map, these are called the weights of the network. So then the whole network is just, again, you apply the affine linear map, activation function, and so on. Just in the very last layer by convention, you do not apply the activation function. And then how do you measure the complexity of such a network? You have the number of hidden layers, which is just the total number of layers which are not input or output layers. Then you have the total number of neurons, which just counts how many neurons are there among all the layers together. And the number of weights just counts how many connections are there between different neurons. And this corresponds to counting the total number of non-zero entries in all of these matrices, which tell you how to go from one layer to the next. Okay, so this is what a real valued, and if you want, fully connected neural network is. And in this talk, I mostly want to talk about complex valued networks. So in these, basically, you replace everywhere the real numbers by complex numbers. So what you do is, in these maps, which tell you how to go from one layer to the next, you now consider matrices with complex entries and vectors with complex entries, and your activation function, which I now by convention call sigma instead of rho to make more clear the difference between complex and real networks, also goes from the complex numbers to the complex numbers. And of course, then the whole network also computes a function from C to the something to a different power of C. And now you might ask, okay, why are you doing this? Or why are some people doing this? You could just as well identify a complex number with a 2-entry vector over the real numbers, and then use your favorite real valued network to compute functions this way. You can do that, but it will give you two different things. The reason is, so the first reason is, if you identify C with R2, then still not every real linear map comes from a complex linear map, right? Being complex linear is more restrictive than real linear. And on the other hand, you have much more freedom in choosing the activation function. The activation function is now a function going from C to C, whereas before it was a function going from R to R. And this makes, as we will see, these complex valued networks much more interesting, at least mathematically, to analyze. Yeah, and the talk, as the title says, is concerned with studying the approximation properties of such complex valued networks. And to properly appreciate this, let's first review what the corresponding properties of real valued networks. And one of the main results in this area is the so-called universal approximation theorem, which in one sentence can be summarized as follows. So multi-layer feed-forward networks with a non-polynomial activation function can approximate any function, where you have to interpret the any correctly. So by the way, this is a very nice paper, and a lot of what I'm going to talk about is mainly generalizing what happens in this paper. This is non-trivial, the generalization, but still many ideas come from here. So what does this now mean precisely? So I will say that a function class F of functions going from Rd to R, which could be a class of universal, but could a class of neural network, sorry, but could also be something else. I call that universal if, using functions from the class, you can approximate any continuous function arbitrarily well, locally uniformly. So whatever continuous function you give me, and whatever error you want to achieve on any compact set, you need to be able to find one function which on this compact set achieves approximation error epsilon. Okay, so locally uniformly, you can approximate every continuous function arbitrarily well. And then this universal approximation theorem, which is proven in this paper, shows that if your activation function is continuous, and if you consider the set of all shallow networks with this activation function, so you allow it to be arbitrarily wide, to have arbitrarily many neurons on the hidden layer, but just one hidden layer, then this class of functions is universal if and only if the activation function is not a polynomial. And I mean, this has two directions, right? It's if and only if. And one of the two directions is rather elementary. So if you have, or if your activation function is a polynomial, so how does a shallow network look like? It's just a sum basically of dilations and shifts of the activation function. So if you dilate and shift a polynomial, it's again a polynomial of the same degree. And if you take a sum of such polynomials, it's again a polynomial of the same degree. So this means if your activation function is a polynomial, all you can ever build with such an activation function are polynomials of the same degree at most. So this can never be universal. So the non-trivial part is showing that if you are not a polynomial, then you can approximate everything arbitrarily well. Okay, and just two remarks. So this, as I stated now, is just for shallow networks. The exact same result also holds for networks where you have an arbitrary number of layers, but fixed. So you fix the depth once and for all, could be 10,000. Then the exact same theorem statement is still true. And the other thing is here, it's assumed now that the activation function is continuous. You can weaken that a bit. It's actually enough if the activation function is locally bounded. And if you look at the set of all discontinuity points of rho and the closure of that, if that's a null set, so if it's not too discontinuous, let's say, then the theorem still applies as stated. Just you have to replace being a polynomial with not being a polynomial almost everywhere. Okay, so this is the real valued universal approximation theorem. And also in the real valued setting, there are more quantitative results. So for example, Mashkar proved that if you have a smooth activation function, but which is not a polynomial, for example, this classical sigmoidal function, and if you want to approximate Cn functions in d dimensions or in input dimension d, then you can achieve uniform approximation error up to error epsilon using a shallow network with this smooth activation function, which has only epsilon to the minus d over n neurons. So this means if the dimension is very large, you run into the curse of dimension, but this is unavoidable in general. But if the smoothness is very good, then you won't need as many neurons. Okay, and as I said before, nowadays people use this ReLU activation function mainly in practice, which is not smooth because of this kink at 0. But still, a variant of this result is still true, as Jarodsky recently showed. So if you use the ReLU activation function, then exactly the same result as before is true with the following modifications. You now have to use a deep network where the depth grows logarithmically as epsilon goes to 0. And up to a log factor, you still get the same number of neurons and weights in total. And there are also variants of this result, more recent, where you can make do with a constant depth, but you cannot do the same with shallow networks. So you still have to have a bunch of layers, which does not need to grow to infinity as epsilon goes to 0, but still you cannot do it with shallow networks. Okay, and the main question of the talk is generalizing this universal approximation theorem and this result to the complex valued setting. And before I do that, let me briefly tell you that people are actually using complex valued networks also in practice, and that they are interesting there. One paper is by these three guys, which is called Better Than Real Complex Valued Neural Nets for MRI Fingerprinting. And what they want to do there is they take complex valued MRI measurements, and based on the measurements, they want the network to determine is the tissue that we are looking at benign or malignant. And what they find in the experiments is that complex valued networks outperform real valued networks for almost all of the experiments. And this is not just because somehow complex valued networks have twice as many parameters as the real valued networks of the same size. So in this case, they really have an advantage. And the other application is for so-called recurrent neural networks, which are used, for example, in language translation. So there, I mean, if you have, for example, an input sentence, it consists of multiple words, right? And what you do with a recurrent network is in each step, you put in one word into the network, and then the network will give you an output and will give you a hidden state, so to speak, which then in the next iteration, you give the network again the hidden state and the next word, and will produce an output and a hidden state, and you go on and on and on. And if you do that, it turns out that in practice, you run into the so-called exploding or vanishing gradient problem. So roughly speaking, you can imagine if you have a matrix and you apply it again and again and again, it will either explode or go to 0 unless it's a very special like unitary matrix. And this is roughly speaking what's happening here. And these authors here are proposing to fix this problem to a degree using complex valued networks which have unitary matrices telling you how to go from one layer to the next. And what they write is that while complex methods or representation systems and so on based on complex numbers have been very successful in signal processing, this is not the case in the deep learning community. And they see their paper as one of the first trying to exploit this the possible benefits of complex valued networks. Okay, so with this motivation, let's go down to the actual results. So this is the universal approximation theorem for these complex valued networks. And before I say anything else, I should say whenever I talk about differentiability in the following, it's always understood to be differentiability in the sense of real variables, so not holomorphic functions, unless I say it otherwise, which will only happen once. Okay, so how does the universal approximation theorem for complex valued networks look like? So we assume for simplicity now that our activation function is continuous. And then the claim in the shallow case, let's begin with that, is that if you look at the set of all shallow networks, so with one hidden layer but arbitrarily wide with this activation function, then this is universal if and only if sigma is not something. And now the question is, okay, what is something? So as in the real case, there we could understand if, for example, the activation function is a polynomial, then we have problems. And here there's something similar. Okay, if you have a polynomial, then you will also have problems. But even more, if you have any holomorphic activation function, then the whole network will always also compute a holomorphic activation function. And you know that the locally uniform limit of a holomorphic function is again holomorphic. So if your activation function is holomorphic, you will not be able to get universality. So one might guess that the answer is sigma should not be holomorphic. This is not quite correct, however. The correct condition is sigma should not be polyharmonic. Okay, so now what's polyharmonic? You know what harmonic is, right? That's just the Laplace of the function is 0. And polyharmonic means that the function is smooth and some power of the Laplacian of g vanishes, where we just use the classical Laplacian in identifying C with R2. Okay, so again, polyharmonic means some power of the Laplacian of G is 0. And if this does not happen, then we get universality, I claim, and this is if and only if. So and just as one more, maybe more constructive characterization, so you can show that the function is polyharmonic if and only if both real and imaginary part of the function are of the form real part of such a sum, where you take the sum of products of an entire function with z bar to the k. So you have entire times z bar to the k. So this is not holomorphic in general, but still the real part will be polyharmonic. And these are actually the only functions which are then polyharmonic. Okay, and this one was now for the shallow case. And remember, in the real valued case, it didn't matter how deep your networks were. It was always the same condition. It should not be a polynomial, the activation function. But here, this is not so. So here, the deep case is really different. So if you look at all networks of a fixed depth, which should be at least be 2, so you have at least 2 hidden layers, then it turns out you get universality if and only if sigma is neither holomorphic, nor anti-holomorphic, nor a polynomial in Z and Z bar. Okay, which is somehow interesting. The two conditions do not match. And you can actually show if a function is not polyharmonic, then it also does not satisfy these conditions. So if you're shallow universal, so to speak, then you're also deep universal. But the converse is not true. For example, this activation function here, z bar times e to the z, is polyharmonic just by this kind of characterization here. But it's neither holomorphic nor anti-holomorphic nor a polynomial. So this means with deep networks, you get universality, but with shallow, you do not get this for this kind of activation function. Okay, so I should say some partial results regarding these observations here were already known in the literature. So for example, these people realized that if you have a holomorphic activation function, then you cannot get universality. And they showed for a very special activation function that you do get universality, but it was nowhere close to a characterization like here. Okay, now the question is, how can one prove this, or how can I at least convince you that it's probably true? And to do that, I will need 2 ingredients. The first is the so-called Wirtinger calculus. So here we identify functions going from C to C with a function going from R2 to C, which just maps xy to f of x plus iy. And then the 2 Wirtinger derivatives, del f and del bar f, are defined like this, where now this del 1f is the derivative, the real derivative in the sense of real functions with respect to x. And del 2f is just the derivative with respect to y. So now the question is, okay, I can of course define these differential operators, but why would I do that? And the answer is they have very nice properties. The first one is you can show if you have a real differentiable function, this is holomorphic if and only if del bar f is 0. And if that is the case, then del f is the usual complex derivative. And the second property, which is important for us because we will be working with polyharmonic functions, so the Laplace is very important for us. You can represent the Laplace operator as del bar up to this constant factor. And then they also satisfy a form of the product in chain rule, but this is not too important for us right now. I mean, if you want to really understand every detail of the proof, you need these properties. But if you're just interested in the ideas, then these two properties are more than enough. Okay, so this was the Wirtinger calculus. And the second derivative is called Weil's lemma. And this says the following: if you have a distribution, so it could be a locally integrable function, but it could also be a delta distribution or whatever, which satisfies that the Laplace of your distribution is f, where f is a smooth function, then actually gamma itself is already smooth, so it can actually not be a Dirac delta or whatever, and has Laplace 0. And by induction, I mean, this tells you that if the Laplace of a distribution is smooth, then gamma itself is smooth. And by an easy induction, you can show from this that if you have any L1 log function, or in fact any distribution, which is polyharmonic in the sense of distributions, so it satisfies that the distributional Laplacian to the m is 0, then actually it is a smooth function, which is polyharmonic. Okay, and why is this interesting for us? Because this condition here plays very nice with limits. So if you have a function, a sequence psi-n's, which all satisfy this, and they converge locally uniformly to some psi, then the limit will also satisfy this condition, right? And using this observation, you can show the following. If you have a sequence of polyharmonic functions with a fixed degree of polyharmonicity, if you want, m, and they converge locally uniformly to something, then the limit is again polyharmonic. So this is somehow related to the fact that if you have a locally uniform limit of holomorphic functions, then the limit is again holomorphic. And this we will use quite a bit. Okay, so like holomorphicity, being polyharmonic is also preserved under locally uniform limits. Okay, now we can actually prove the two directions. So we have to prove necessity and sufficiency, right? So if the function is polyharmonic, then we want to show that universality fails. So how do you do this? So each shallow network is just such a linear combination of sigma composed with an affine linear thing. And just because it's somewhat easier to work with one variable function instead of d variable functions, let's fix the last d minus 1 variables, and let's just look at it as a function of the first variable. This is then of this form, so you have a sum of shifted and dilated versions of sigma. And now you can, by an easy calculation, using this representation of the Laplace operator in terms of Wirtinger derivatives, you can show that this implies if your activation function is polyharmonic, then actually each shallow network is also polyharmonic with respect to the first variable. So this is really not too difficult. I mean, I'm not showing it here, but you can, that's an easy calculation. And then we just saw that if you have a locally uniform limit of polyharmonic functions, then the limit is again polyharmonic and in particular smooth. So this means you can never approximate a function which is not smooth. So universality fails if you are polyharmonic. Okay. So then we have to do the same for deep networks. So for deep networks, we had 3 problems: being holomorphic, being anti-holomorphic, and being a polynomial. So if you're holomorphic, then the whole network will be a holomorphic function. And locally uniform limits of holomorphic functions are holomorphic, so you cannot get universality in this case. If sigma is anti-holomorphic, then you can also convince yourself that the full network will be either holomorphic or anti-holomorphic, depending on how deep your network is, so if the depth is even or odd. And with similar arguments, you can then see that universality fails, because the limit will also be holomorphic or anti-holomorphic. And the last property is if you have a polynomial, okay, then the full network will be a polynomial where the degree only depends on the depth of the network and this polynomial P. And with polynomials of degree up to 10,000, you can also not approximate everything. Okay, so this shows necessity. So now the remaining question is, how do you prove sufficiency? So we want to show that if your activation function is not polyharmonic, then you can actually approximate everything. And to show that, I will assume that the activation function is smooth. One can remove this assumption via a modification argument, but the main ideas are contained in this case. So this is why I'm assuming it here. Okay, and the first step is to show that it actually suffices to work with 1D input. So the claim is if networks with input dimension 1 are universal, then this same holds for any input dimension. And I'm not showing, I'm showing the proof here, but I will immediately skip it. So if you're really interested, you can watch the recording of the talk and look at the proof, but otherwise I'm skipping it now. Okay, now we just have to work in the one-dimensional case, and we want to see that if the activation function is not polyharmonic, then with shallow networks, we can approximate everything. And the main auxiliary result to get this is this claim here. So if some mixed Wirtinger derivative of sigma is non-zero, then the corresponding monomial z to the m, z bar to the l can be approximated arbitrarily locally uniformly by shallow networks. So how do you do this? So you look at sigma of wz plus theta, and then you take a mixed Wirtinger derivative of this, exactly this one, but with respect to w. And if you do the computation, you then see that you get out this monomial here. You're taking derivatives with respect to w. So this constant factor here comes out times this. And now you evaluate everything at w being equal to 0, and then you get exactly the monomial that you want to have times this constant number. And by choosing theta suitably, because you assume that this Wirtinger derivative does not vanish, you can then get this monomial here. So what we're doing is we're using the Wirtinger derivative to extract monomials, if you want. So then the last step is just to show that you can approximate this shebang here using neural networks. So how do you do that? This here is a neural network, right? And you're just taking a derivative of that. So the idea is to show, or to, the definition of the derivative is it's a limit of difference quotient, right? So now let's, for example, consider this derivative here. This is the limit of a difference quotient. And as a function of z, this is just a neural network. This is just a neural network. So the whole thing is a neural network. And since the convergence here of this limit is locally uniform, you can show that this means that this derivative here will belong to the closure of this network set. And you can then extend that to higher derivatives by taking higher order difference quotients, which are again just a linear combination of shifted and dilated sums of sigma. Okay, and the corollary is the universal approximation theorem. If sigma is not polyharmonic, then you get universality. Why? Because if sigma is not polyharmonic, remember you can rewrite the Laplacian as del del bar. So this mixed derivative is non-zero, and then also all lower order derivatives are non-zero, because otherwise this one would also be zero, right? And this means you can then get all monomials, and once you have all such monomials by Stone-Weierstrass, you get everything. Okay, so this proves the thing for the shallow case. So now the question is, how does the weaker condition come in for deeper networks? So let's assume our activation function is not holomorphic, not anti-holomorphic, and not a polynomial. And why the hell can we then approximate everything? So as before, sigma is not holomorphic. So del bar sigma is non-zero. And as before with this proposition, this means you can extract the map z maps to z bar. But also sigma is not anti-holomorphic, meaning that this derivative is non-zero. So then you can approximate z maps to z arbitrarily well using shallow networks. So just by adding the two, you can then approximate the real part arbitrarily well using shallow networks. Okay, now we have not used up to now that it's not that the activation function is not a polynomial. So being not a polynomial, you can show it's not too difficult to see that this is equivalent to having for each m either this Wirtinger derivative non-zero or this Wirtinger derivative non-zero. You don't know that both are non-zero, but at least one of the two is non-zero. Okay, so if this is non-zero, by the proposition from before, you can approximate using shallow networks the power z to the m. And if this is non-zero, you can approximate z bar to the m. All using shallow networks. And now the idea is we just put the two together because we have deep networks, right? If a deep network, you can use one shallow network and then another put behind each other. And since this here is a real function, we don't really care if we have z bar or z bar to the m, z to the m or z bar to the m, right? So this means by composing the two, because we have at least two hidden layers, we can approximate real part of z to the m for arbitrary m. And then you again get you easily from this universality. Okay, so long story short, if you didn't like the proof or didn't understand too much, the result I think is very nice. You have universality if and only if you're not polyharmonic in the shallow case, and if and only if you have this condition in the deep case. And how did the proof work? Some weird trickery using Weil's lemma and Wirtinger derivatives, right? Okay, so the last part, let's get to the quantitative bound. So here we ask, given a function, how big do you actually have to make your network to achieve a decent approximation? And this is joint work with a bunch of people from Eichstätt, Sande Karaja, Digwan, Johannes Mali, and Götz Pfander. And here we are working with the so-called modReLU activation function, which is the generalization of the ReLU to the complex case if you want. So the idea is you look at the soft thresholding function from the reals and you extend it radially to all of C. So then it looks like this. And we work on the complex unit cube. So these are all vectors Z and CD, where all real and imaginary parts are between 0 and 1. You can also do that for more general domains, but this is the simplest. And then the claim is, if you have a Cn function on this d-dimensional complex cube, then you can approximate it uniformly up to error epsilon using such modReLU networks with this many non-zero weights and this depth. So this is very close to the result by Jarodsky. The difference is, okay, here we have a power 2, which you can maybe remove. And we have epsilon to the minus 2d over n. So why does this come in? Why 2d and not d? This is just because CD is r to the 2d, if you will, right? Okay, so how does okay? So two more details, which I will not skip. So that you can actually choose the architecture of the network to be independent of the function you want to approximate. So just the choice of the weights will change. And the other thing is you can actually choose the weights. So each weight of the network will be bounded in absolute value by epsilon to the minus 44d. So we didn't really try hard to optimize this, but it somehow blows up at most polynomially in epsilon. And how does the proof work? So you first show that such networks can approximate the product quite well. Then you show that they can also approximate a partition of unity. And this then allows you to implement locally the Taylor polynomials of f, which you can then use to approximate f. So this is roughly the idea with a lot of technical details hidden. And of course, you could now think, okay, I will sit down today, this afternoon, and prove a much better result than these guys. So the question is, for example, this here the optimal rate that you can get? And the answer is more or less yes. So if you restrict to networks where each individual weight blows up at most polynomially as epsilon goes to 0, and if you look at networks where the depth grows only like a power of the logarithm of 1 over epsilon, then the rate is optimal. So you can never achieve approximation error epsilon uniformly over all Cn functions with all derivatives bounded by 1, using networks where the number of weights grows strictly slower than what we have in our result. If you insist on the depth not growing too crazily and the size of the individual weights not growing too crazily. So how do you do that? This is based on an entropy argument, which essentially means you count covering numbers. So what is a covering number? The covering number of a set is of radius epsilon. You count how many balls do you need of radius epsilon to cover the whole set. So what we do is we bound the covering numbers of the set of all such networks. And we know already how the two epsilon covering numbers of this set of target functions behaves. So now if you could approximate all functions f in the target set this well, and you could cover the set of all networks by, let's say, 50 balls of radius epsilon, then you could cover the set of all target functions also by 50 balls of radius 2 epsilon. Right? And by putting all these observations together, you get this kind of result. Okay, so with this, I would like to close and thank you very much for your attention. So what did we see? We saw the universal approximation theorem generalized to complex networks, which involved some, at least I think, quite nice properties of complex valued functions like this polyharmonicity and the Wirtinger derivatives. And in the last part, I briefly told you about some more quantitative results for networks with this modReLU activity.